Hello and welcome to the material on chemical kinetics. And chemical kinetics is some of my favorite stuff. And it turns out that a Big Mac contains about the same amount of energy as a stick of dynamite. And yet when you eat a Big Mac, you release the energy over a much longer time scale. However, when you light a stick of dynamite, boom, it can blow up in a fraction of a second. So what's kind of interesting here is that although it's the same energy, it's a different rate of reaction. It's a different speed. And chemical kinetics deals with speeds of reaction. So that is essentially what we mean when we write chemical kinetics. So it is the rate, okay, or speed of chemical reactions. And clearly it matters whether we are releasing the energy, in dynamite in a fraction of a second versus a Big Mac over, fractions of a day. So what exactly do we mean by the speed of a reaction, right? I mean, with a car, we know that the speed is probably the number of miles you're driving divided by the number of hours over which you drive it in, so miles per hour. So what exactly do we mean by a reaction speed or a reaction rate? So we have to define it carefully. So we're going to say that the rate of a reaction is going to be equal to the change in the concentration of something. So normally the molar concentration. All right, square brackets, and that's going to be divided by the change in the time over which this occurs. So it's going to essentially be the change in concentration, so delta concentration, over the change in time, delta T. So it's clearly going to have units of whatever these concentrations and times have units of. So we're going to probably measure concentration in molarity and time in seconds. So the rate of a chemical reaction is going to have units of molarity per second, right, which we can write like that, or we can possibly write it molarity seconds to the -1. Now, if we try and apply this to a chemical reaction, so for instance, let's look at the reaction between nitrogen and hydrogen that goes on to form ammonia. And so far we've defined the rate of the reaction as just the change in concentration over the change in time. One initial problem, of course, is that these concentrations are going to decrease, and on the right-hand side, these concentrations are actually going to increase. So immediately, if we define our rate as just the change in concentration over the change in time, we'll get a positive value for the ammonia, and we'll get a negative value for the nitrogen and hydrogen, because these are increasing in concentration, so the top will be positive, whereas these are decreasing in concentration, so the top will be negative. We also have to be a little bit careful here, because if you look at the coefficients, we'll see that the hydrogen is used up 3 times as fast as the hydrogen, and the ammonia is made twice as fast as the nitrogen. So if we look at the nitrogen, every time we use up one of these, we will use up 3 of these. So this rate will be, or this change in concentration will be triple that of the nitrogen. However, for every one of these we use up, we will make 2 of these. So that rate will be double. So because of that, right, we don't want to have to say, well, this is the rate with respect to nitrogen or hydrogen or ammonia. We are going to go ahead and define rate in such a way as it doesn't matter what we look at. And here's how we're going to do it. So we're going to go ahead and we're going to start off by saying rate equals the change in concentration over the change in time. So we got the change in concentration of nitrogen. Okay, we got the change in concentration of hydrogen over the change in time, and the change in concentration of ammonia, right, NH3, over the change in time. So we've got to do a couple of things here. One is that because the nitrogen concentration is going down, this will be negative. And we often like positive numbers in chemistry and actually in everyday life. So we're going to go ahead and we're going to put a minus in front of here. And because the concentration of hydrogen is also changing, we're going to put a minus in front of the second expression to make it a positive rate. And if you look at the ammonia, the concentration is going up, so it's already going to be positive, but just to kind of keep things straight, right, we can write a plus there as well. The hydrogen is being used up 3 times faster than the nitrogen, so we're going to divide the rate of change of this one by 3 in order to equalize it with the nitrogen. So we can divide it by 3, or we can think of it as being multiplied by 1/3. If we look at the ammonia, we can say for every 1 nitrogen being used up, we're making twice as many ammonias. So this looks to be twice as high as it should be. So we have to multiply it by half, which is the same as dividing by 2. And just to go ahead and keep things straight, right, we can write minus 1 over 1 in front of the nitrogen. So essentially you can see a couple of factors here. So the bottom of all these fractions is essentially the stoichiometric coefficient. So if you look at the chemical equation on the top right, so the 1, the 3, the 2 appears here as the 1, the 3, and the 2. And the other thing is it's negative for reactants and it's positive for products. So we just have to remember that we have a minus sign anytime we've got a reactant because its concentration is going down. We need to flip the sign in order to get it positive. And we're going to have a positive sign every time you've got a product because we are presumably making products. So we need to just leave it unchanged, which is what multiplying by +1 does.